Cool. So the name of this talk is Visualizing Rubik's Cube with Python. The two links here are shown as well. They're pasted in the chat if you'd rather just click them. So first, I'll start off with a little bit about me. My name is Dustin Haffner. I'm a senior software engineer at Netflix. I'm based in Oakland, California. As well, Netflix is based in Silicon Valley. It's all generally the same place. I've been at Netflix for about 3 years in December. I'm Nigerian American, born and raised in America, but I spend time in Nigeria when there's not pandemics going on. So I always like to do things that address, both my love of programming and my love of Nigerian culture, West African culture, etc. I've been a Python user since Python 2.6, but as we all know, that doesn't really mean anything. It's all about the code you write now, and some of the best programmers are those newer ones. But that's when I started using Python, and I've been using it ever since. It's my favorite language. I don't even use it too much on the job, but for hobby code and etc., I love to use Python. And you can find me at dhaffner on most social networks, Twitter, GitHub, LinkedIn. You can Google my full name. Always welcome to connect with me. So cool, I'll get into the talk now. So first, I'll talk about the goal. And this is kind of a goal relevant to this talk, but a goal I think more relevant to personal projects in general. Exploring new tools, on a day-to-day basis, we don't always get the chance to use the coolest new thing or use the coolest new framework or tool. So it's always fun to take personal projects as an excuse to do that. So in this project, my goal was to explore GraphQL, network visualization, so displaying graphs, displaying nodes, edges, etc., and play with React JavaScript. This is a Python talk, but at times we need to write front ends and we need to write code that runs in the browser. So naturally, we all tend to JavaScript. So just a quick overview of this talk. I'm going to talk a little bit about Rubik's Cube, what it is, for anybody not familiar or who hasn't played with one. I'll talk about graphs as a concept. I think we all know graphs in day-to-day life, but I'll just give a quick definition. And then I'll talk about CubeGraph, which is this code I wrote to kind of tie together these two concepts, the Rubik Cube and graphs in general. So let's jump into it. First, I'll show what a Rubik's Cube is. So this is a solved Rubik's Cube. It's actually mine. I have the scrambled version here. But Rubik's Cube is invented in 1974 by a Hungarian named Erno Rubik. It can be scrambled in 43 quintillion ways, and that's just a huge number. I wrote it out just to emphasize it's 1 followed by 18 zeros, times 43. And there's many variations on the cube. The one pictured here is the 3x3x3. There's the 4x4, 5x5, etc. There's Sudoku cubes, puzzle cubes, all types of varieties. But it's a popular puzzle. It's for me, I like it because it's sort of simple in concept, but it's not actually trivial to solve until you learn it. Then it feels easy, like most things. So now I'll digress a bit just to talk about cube notation, which is relevant later in these slides. So breaking it down, the Rubik's Cube has 6 faces. We denote them by kind of their orientation. So L for left, F for front, right for the right face, and so forth, bottom, down, upwards. Each of these faces has 9 squares. And going in order of certain faces, U, R, F, D, L, B, we can encode any scramble of the cube with 54 letters just by ordering out each face color from 1 to 54. So below, at the bottom of this slide, we see an encoding of the solved cube, right, as a string of 54. So going on, I'll talk about turn notation. So what is a turn in terms of a Rubik's Cube? A turn is a rotation on a face. So to the right here, we see 4 examples of turns: a right turn, a right prime, which is to mean right, turn the right face 90 degrees clockwise. I'll demonstrate it here also on camera. Just a simple turn. And R prime would mean the same turn, but the other direction. And similarly, we can use U2 to say turn this face turn this upper face 180 degrees. So the utility of that is you can list out lists of turns to describe any scramble state of the cube, right? If I tell you to take the cube and do this series of turns, I can tell you what cube you'll end up at. So it sort of forms a path. And with that notion, we'll touch on graphs briefly. So we might all come to this with a different understanding of graphs, but just to get us all aligned, just give a quick example of a graph here as we talk about just a series of circles and lines, basically. So the fancy Wikipedia definition you'll find says mathematical structures used to model pairwise relations between objects. But concretely, in this picture, that means that, okay, let's take the nodes of the graph to be these numbers, 1, 2, 3, 4, 5, 6. And then we see that between certain numbers, there's links. Those are the edges. They join two nodes, or two numbers in this case. And we see some examples of edges, 4, 6, 4, 5, 5, 1, and so forth. And in some graphs, edges can be given a direction. So the classical example of this would be Google Maps, or anything that does specific routing, flight itineraries, etc. And we see an example of that directed graph with edges to the right on this slide. Cool. So math definitions out of the way. What we're here to do is tie this together. And with that, that would be with cube graph for me. Before this, I'll just talk about, how did I come up with this idea? I've always been, I guess I learned how to solve a Rubik's Cube in college, and I've always been kind of a nerd about it. I studied math in college, but I love the Rubik's Cube because it's a good puzzle, and having a puzzle that you can always solve, I feel like it gave me a quick route to get out of a mental block, or a creative rut. If I'm dealing with a bug that is racking my brain, I can solve a Rubik's Cube real quick and hopefully clear my mind enough to get an insight to keep pushing onto that problem. So that's kind of what sparked my interest in exploring this Rubik's Cube via code. So just a quick visualization, almost a preview of the app itself that I wrote. So now we get to visualizing the cube graph with Python. So first, what does this mean, cube graph? Well, I've just described what a Rubik's Cube is. I've just described what a graph is. So let's tie them together. So let's call the cube graph the graph in which all Rubik's Cube states are nodes, and those nodes are each connected by one move. So essentially meaning you can get to node A from node A to node B by turning the cube in some direction. And with this definition, let's make the goal to visualize this cube graph in interesting ways. So how do we do that? First, now let's talk about the anatomy of the app itself. Backend first, API first. I chose to use Flask and GraphQL, and you might see an asterisk on that GraphQL, and the only reason is because it has the word graph in it, and because it's a shiny new tool in the industry, and I wanted a reason to learn it and play with it, at least in Python. So with that, I started the backend first, the GraphQL server, and I started schema first, which if you dive into GraphQL, there's a heavy emphasis on describing your data first before you implement it. So you kind of get the picture straight in your head. So working from our previous definition on cubes, we say cubes are 54 character strings, and that in GraphQL, we will take a query to get a path between any two cubes. So this is using GraphQL parlance, where I describe a type and then I describe a query on that type. And to do this, I used a pip package called Ariadne that exposes GraphQL utilities in a really clean way. So I'll show a code example, just a plain screenshot from VS Code of this schema that I used. So basically, you see three types here: type query, type cube, and type step. And this is essentially just giving me the machinery that I need to ask, how do I get from cube A to cube B? And what steps do I need to take there? So concretely, cube is our node, and step is the edge that might connect nodes. So what does this look like in code? So again, the picture of the schema itself, we know that ultimately we're talking Python here. So what does that look like in Python? So to the right is the implementation of the schema, and anybody who's familiar with Flask or has played with any framework that makes heavy use of decorators should look at this code and feel familiar. And that's exactly how I felt when I first saw it. I said, okay, I can just write some functions and then tie them to the fields that I define in my GraphQL schema. That's easy enough. And really, the entire server is essentially shown in these like 40 lines of code. The only omission was, the small amount of glue code to make it work with Flask, which was very nice. So again, Python tooling saves the day and lets me focus more on the task that I want to do. So with those pieces together, what an example GraphQL query look like? And again, you're free to click this GraphQL link and try it out yourself, but I'll show, just an example call and response on the screen as well. So this is a query as defined on the last slide, a path to get from a source to a target node in this graph. And I'm essentially saying this is a query, and the query I'm calling is path. Here are the arguments, source and target. And I'm asking from the response, I care about the move, source, and target fields. So we can see what that example response looks like on this next slide. So one of the niceties of GraphQL that I love is your query shape essentially matches your response shape. So we see in the query, if I go to the previous slide, that I'm asking for a path and I'm saying, give me move source target. And then my response shape is exactly that. It's an object with a field called path. And in that path is an array of move source target objects. So your response shape essentially matches your data shape, which I think is very nice, a nice design of GraphQL. So with that out of the way, the GraphQL server will consider it implemented, at least at the schema level. So we know that at some point we actually need to solve the cube. We actually need to find that path between cube A and cube B. So with that, I used another Python package by a man named Kosiemba, or an algorithm by a man named Kosiemba. And there's a visualization of that algorithm in play on the right here. So the cool thing about it is it works very fast. It finds your solution path literally in milliseconds. It doesn't feel like any lag at all. It's a graph-based search, IDA star, using heuristics to find shorter paths. And for me, it's fascinating in a theoretical perspective because we know this state space is super large, 43 quintillion. And this algorithm is essentially searching that in almost no time at all. So how I use it in Python, how we touch it in Python is very simple, and I love it. I love this API. Is perfect to me. Whoever designed this, I give them kudos. So I showed an example usage at the bottom of the slide. Import Kosiemba, and then just pass your cube state to kosiemba.solve, and you get your algorithm. So it's perfect, and it was the perfect building block for me to make this project. So how do we tie those together and visualize that on the front end? So for the front end, I used React and Apollo Graph Tools. Maybe a lot of people have played with React a little bit, but if you haven't, it's currently like a really popular framework for working with JavaScript and creating components in the browser. And it plays well. It has a lot of nice integrations with GraphQL, especially via Apollo. So with the GraphQL server out of the way and the cube solver integrated, we move on to the cube UI, right? So we don't want to just show a random graph in the browser. We want to show an actual cube. So at the right here, I have a quick animation or a quick screen cap of the cube solver in play, kind of an early iteration as I was developing this, of me just executing turns on the cube. And that's essentially what I wanted. That was like my first personal milestone for this. Like I just wanted a cube in the browser and buttons to execute turns. I didn't really care about gesture controls on the cube itself, but I wanted to be able to execute turns. And I also wanted to show a list of turns that will get me to the solved cube. So in this example, in this video, all I'm doing is looking at this list of turns that pop up and executing them. So you can see I finish here with U2, and then B2 solves the cube. Boom. So that's all I wanted. That was the first milestone. And then after I was satisfied with this and this worked properly, I wanted to graph it, right? I wanted to tie this together with the graph. So I essentially took that code, and to the right of it, literally to the right of it, I just put a force graph that was built as the cube is turned. So we execute a turn, we get to a new cube state, we update the graph. That's essentially the feedback loop here. And then the current cube, the cube displayed on the screen, is always in purple. Here the neighbor cubes are pink, neighbors being those cubes one turn away from your current cube. And then any path that gets calculated, whether it be from one cube to another or one cube to the solved cube, they're always highlighted in blue. So this was my first iteration of the graph. Thanks, Vince. Appreciate that. And yeah, so essentially when I got to this point, I felt like, okay, mission accomplished. Like, this is pretty. And then I just spent a little bit of time cleaning up the UX and the user experience and some of the bugs that I introduced in the front end code. So with that, I'll talk about, just give an inventory of both Python modules and front end code used, and then we can look at, I guess, the current version of it. So as I spoke of, Cosiemba, and the algorithm for solving the cube, a module named PyCuber gave me a cube object that I subclassed and added a few methods to, and pretty much was good to go. Ariadna is the library that I use for implementing the GraphQL server, and of course Flask, the web framework we all know and love, other than Django and others, that works well with Ariadna. And then front end tooling I used React Force Graph for drawing this graph that you see behind this slide. Super easy. So basically, I had to maintain the graph itself, the list of nodes and edges, and then pass that to this component, as well as some display properties. But it wasn't I didn't have to go and write a whole graph library to do this. And then similarly, Apollo client let me interface with my GraphQL server. So I liked it because I got to keep everything separate. I got to make my server in Python like I usually like to do, and then just pass a nice GraphQL API to the front end. I use Material UI to lay out the grid on the page and render some buttons and just generally house everything. And then at the core of it all is React and of course JavaScript. And one cool thing is the cube itself, I found as a web component. So it was fun integrating web components with React for anybody who does framework front end work. That's non-trivial. So it was fun to do that. And the cube itself is fully HTML and CSS, which I like a lot. And it was easy to work with. And then working between Node and Flask, I used proxy server. So with that, I say thank you, and thank you all for listening. I'll switch from these slides to the page itself, and hopefully you all get a chance to check it out, or send me a PR and an issue on GitHub if you see something that could be improved. Yeah, thank you. Yeah, so I'm just showing the current page itself, so feel free to check it out. But yeah, I've obviously I wrote this, but I've spent I'm not ashamed to say I've spent a lot of time just clicking this and just watching the solver in action. It's kind of fun. If you're learning to solve the cube, it could be, you know, kind of a good learning tool as well for demystifying it. And yeah, I don't know. For me, this was a good just exploration, and kind of thinking of Scott's talk earlier of, you know, just doing things and kind of finding the joy in things. I kind of, it rung true to me in doing this. Okay, so I see Vince's question. He says, can I clarify that I'm understanding correctly? The visualization is essentially a visualization of the solution heuristic. No, it's not a visualization of the heuristic. So the graph itself is our actual cube nodes. So what we're looking at here is a path essentially from a random node to a solve node. So let me refresh real quick and get a fresh scramble. So right here, what we're looking at is the output of the algorithm. So the algorithm says essentially take these steps to get to the solve cube, and then we're just displaying those intermediate nodes. Path from a random node to a solve node. So that yeah, that's correct. That's the path that the heuristic took. This is the path that the algorithm that figured it out. Yeah, sorry, I misunderstood your initial question. Great question. Yeah, and it's kind of cool as well. There's buttons up in the right for adding random cubes, and it's fun to see kind of where the algorithm goes astray or where the algorithm doesn't follow the same path. Uh, but yeah, it's cool. So like right now, I'm on a random cube. It's right here, right? This dark one is my current cube. And if I click any other cube, I make the algorithm generate a path to it, and then those new nodes get added. But then if I'm at this cube, this cube here, and let's say I click up a node that's already in a path on the screen, you see that the algorithm takes essentially the same path, but there's one node that it diverged on, which I think is pretty interesting. You know, I wish I knew what was going on deep under the hood, but yeah, so it's a fun thing. Yeah, thank you all for joining me. Any other questions? Awesome, go for it, Vince. Yeah, that's a great question. Yeah, my only the first thing I think about when I so the question that Vince asked was any thoughts of expanding this to 4 by 4 cubes or etc. The first thing that comes to mind is the branching factor, just from yeah the number of options that you have for turns on a given face. So on this one, I even like on this cube, I guess from any turn you have, what do we see, 18 possible turns. So for the 4 by 4, I don't even know off the top of my head, but yeah, it would be a fun challenge to try and represent all of the turns that one can make on the screen without overwhelming the user. And then another challenge would be displaying the graph in a way that yeah, that's still visually appealing. Maybe I don't know, maybe that would be fun to draw in 3D, like a 3D graph. This same component that I use supports 3D. I just rather do 2D. But yeah, maybe the 4 by 4 could be visualized in 3D in a cool way. Yeah, that's an awesome idea. Maybe that's PyCon Africa 2021 talk right there. Yeah, you see, you read my mind. Yeah, awesome. Thanks. Yeah, thanks. Yeah, the 2 by 2 would be simpler still, and I think yeah, the 2 by 2 would be fun. There'd probably be, I think there'd be even a fun, maybe a fun challenge in visualizing that, since you'd have less complexity. I've actually I've never solved a 2 by 2. I have a 4 by 4, but I can only solve it treating it like a 2 by 2. So so that's the only 2 by 2 I've solved. I can't solve the 4 by 4. I can solve this one, but I won't be put on the spot. Yeah, you probably could draw the full state space for the smaller cube. Or any of you all cubers? I'll call them cubers. Anybody like to solve the cube just for fun? Yeah, yeah, Nicoletta, awesome. Well, awesome. I'll let's see. I can jump off.